Hello, everyone, and welcome back. So, when we're talking about square roots, powers, and exponent laws, what we want to talk about is what if we have a square root with a non-perfect square? Remember how we said if we have perfect squares underneath the square root, then we're saying, oh, what number multiplies by itself and it's typically a perfect square, the number underneath the square root. Like that's what you've seen so far. What if I don't have a perfect square, right? Like over here, I've done, for instance, square root of 10 or let's say, sorry, square root of, let's say 4, right? Then I ask myself, what number multiplies by itself to give me 4? And so that number is 2, right? 2 multiplies by itself to give me 4. But what if I tell you, for instance, what is the square root of 6, right? There is no number, like there is no whole number that would multiply by itself to give me 6, right? And so what we do here is we can approximate it, right? So we're going to first look at the first strategy to doing this, which is approximating using a calculator. Okay, so that's going to be our first technique here, where you approximate using your calculator. And so if I have, for instance, something like square root of 12, that's also not a perfect square. There is no whole number that would multiply by itself that would give me 12. And so what we do instead is we say, okay, well, we need two rational numbers that would multiply out to give me square root of 12, right? So then in the calculator, what we do is we literally just put the square root of 12 and see what is our answer, right? So now we know that obviously if it's not a perfect square, then we have an irrational number, right? Like as the answer. So this over here is going to give me an irrational number. And so when I put this in my calculator, let's do this together. So when I put this in my calculator, what we're going to get, so square root of 12, we get 3 point, okay, so we get a pretty long one. We get 3.464, and it continues on because it's irrational, right? It's a non-terminating decimal. And so if I were to round this, for instance, to 2 decimal places, I could go, okay, well, 3.46. And so approximately it's 3.46. Now we can round to 2 decimal places. We can round to 1. It really just depends on what the question asks us. So sometimes it will say round to the tenths. This is my tenths position. And so I look at the number before. Okay, 6 is higher than 5, and so that makes me round the 4 to a 5. But if they say, for instance, round to 2 decimal places or round to the hundredths position, then that means I look at this number, the 6, and I go, oh, okay, is the number after it bigger than or equal to 5? It's not, and so I don't need to round it up. I just keep it as 6. Okay? All right, let's look at the next way of doing this. So approximating square roots without a calculator. This is not very common, but it is an important skill because sometimes you want to be able to estimate. Like that's how I do it with in real life when I'm talking to friends or whatever, or I'm tutoring and I'm like, okay, square root of 6, what is this approximately equal to? It's good to be able to know how to do this without a calculator. And so let's say I tell you, for instance, let's do that example, square root of 6. Oh, let's do this example of square root of 6. Okay. Now, square root of 6, although 6 is not a perfect square, it sits between two that are, right? So what are the perfect squares between 6? Let's list some of our perfect squares. List of perfect, am I covering it? Yep, I am. So let's move this a little bit lower. Boom. Let's move it like down here. Yeah, that's good. Okay, list of perfect squares. Okay, so we're going to have our first one, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, right? So 2 squared, I'm just kind of listing them so that you know, like this means that 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25. I'll list a few more. 6 times 6 is 36. Let's do one more. 7 times 7 is 49. Okay. All right. So these over here are our perfect squares. Okay. So I'm going to highlight the perfect squares. I don't want that line beside it. Okay. So these are our perfect squares. okay? The 16, the 25, the 36, all of the ones that I've highlighted, these are our perfect squares. Now, let's have a look at how can I figure out what is 6 if what is the square root of 6 if 6 is not a perfect square? Well, I think about it and I go, okay, what are the two perfect squares that I have that 6 is situated in between? And so we can draw a number line here. Here's our number line. And we can see, okay, well here, if this is 0, for instance, and let's even move the 0 a little bit to the side. If this is 0, and this over here is the square root of 4, okay, so 2. And then the square root of, let's say 9, so 3, okay. So we can see that the square root of 4 and the square root of 9 are kind of sitting in this way. And so square root of 6 looks like it should be a little bit in between, right? Like it's not exactly in between because between 4 and 9, that's 5 units, but between 4 and 6, that's 2. And so it looks like it sits kind of over here closer to 4. And so if I were to round this, I'd say, oh, well, it's not in the middle, so it wouldn't be like 2.5, right? Like if it was in the middle, that would be 2.5. Right? The answer would be 2.5, but it's not in the middle. It's a little bit closer to square root of 4. And so it's a little bit smaller than 2.5. And we can see that we got over here, well, that was square root of 12, actually. We can see that if I do square root of 6, it's going to be like around 2 like 2.4-ish, like it's going to be around there. And so we go 2.4 approximately, okay? There are two ways you can write approximately. You can do like this, you can do like that, or you can do this. These two mean approximately. Approximately. Okay? All right. Okay, so that means that when I want to figure out what is the square root of something without using the calculator, I look at my perfect squares. I set them up on my number line and I figure where is it? Where is the perfect square that where is the square root of the number that I'm looking at? Where does it sit between? Is it closer to the one on its left or is it closer to the one on its right? And I feel like for something like this, we want to do one more example. So let's do that together. Let's move the Pythagorean theorem a little bit lower. How about we try square root of 11, for instance? Okay. And I did say it's approximately 2.4. Let's see what it actually is. Let's go ahead and try on our calculator. So we have square root of 6. So it's 2.449. And so using a calculator, we've confirmed that we were pretty much close. Like if we were to round to one decimal place, it would be 2.4, right? And so that was a really good guess on our part because we saw that square root of 6 was, if we look at the difference between 4 and 9, that's a distance of 5, like 5, that's a distance of 5 units between 4 and 9. And so if between 4 and 6, that was 2. The midway, if it was 2.5, would have been 6.5. And so it should have been a little bit lesser than this 2.5 over here. And so we said, okay, let's estimate it at 2.4, okay? So your estimate can't be like too bad and it can't be, but it doesn't have to be too perfect, okay? But it can't be like, oh, it's 2.9, but that doesn't make sense because 2.9 would be over here. And that means it's like square root of 8. So that's really close to square root of 9, for instance, okay? All right, let's try another one so that you can try it out. So over here, I want to figure out what is the square root of 11? Or let's even do a higher one. Let's do square root of, yeah, let's do square root of, let's say 39. Let's go 41. Square root of 41. What is the square root of 41? Well, I first asked myself, because I don't know yet if this is a perfect square or not. So I go, well, is 41 a perfect square, right? Like, is 41 a perfect square? Can I just have a whole number as an answer? And so I think of my perfect squares. It's clearly not any of these. Nope, nope, nope. But it looks like 41 sits between 36 and 49. And so I'm going to draw my number line again. And you don't have to draw the number line if you can visualize it, but I like drawing the number line because it's just easier to visualize. So if I say, for instance, here's my 0, okay, and we can see that 6, let's say 6 is over here, okay, and 6 would be the square root of 36, right? And then 7, let's say, is over here, and that's the square root of 49. And so I figure out, okay, well, what would be kind of the midpoint? Like I like to figure out where the midpoint is because it kind of helps me navigate. Like if I say the midpoint over here, right? Let's do the midpoint in green as well. So the midpoint at 6.5, what's the middle between 49 and 36? Well, I can do that. I can go 49 minus 36 divided by 2. And so I get, let's see, 4 and 9, that's 13 divided by 2. That is approximately 6.5. So 6.5 digits. So this would be like 36 plus 6.5, right? And so I would go, oh, okay, well, another way you could have done this is kind of gotten the average. And so you could have done, I was seeing how many units between them, but you could have done this and then divided by half. I found that kind of the subtraction is an easier way for me to just figure out how many digits are in between them. So so it looks like it's at 6.5. And so the distance between it would be 6.5 digits. And so I go, oh, okay, well, that's going to be like 36 plus 6. That's going to be 42.5. So this is 42. Sorry about that. This is like around 42.5. Okay. And so I know that 41 sits before that by a little bit, like it sits over here. And so I could again make an estimate that it's around like 6.4. 6.4. We can try that out. Let's do 40, the square root of 41. Yeah, I get 6.40. So that's actually a really good estimate on our part. And that's basically how you do it. Now we got lucky that it was the 0.4 on both ends. But again, if I were to do another example, and I'll do one more because I know that this is not an easy topic to kind of wrap our heads around. So let's do one more. If you feel like you already understand it, just move forward in the video to the Pythagorean theorem. Okay, so one last time of kind of covering this. If I do the square root of, for instance, let's say 15. Okay, now 15 I know is not a perfect square because looking at my perfect squares, it's not, but it does sit somewhere between 9 and 16. So let's say this is 9 and this is 16. Sorry. So this is the square root of 9 and this is the square root of 16. Square root of 9 is 3, square root of 16 is 4. And so I go, okay, well, square root of 15 looks like it's pretty close to 4. And so I can make an estimate of saying, oh, well, it looks like it's approximately like 3.9 because it looks like it's very close to 4. So it's like 3.9, for instance. I try this out and you don't ever have to like try it out on your calculator when you're asked to estimate. So I get 3.87, which is pretty close to 3.9. And so that's a pretty good guess and I can leave it at that, okay? All right, let's move on to the Pythagorean theorem. Now, you may have heard that name before because it's a very common name in math, but what is the Pythagorean theorem? The Pythagorean theorem basically tells us this, that if I have a right angle triangle, so let's draw a right angle triangle here. Okay, so it's a right angle triangle. That means that it has a right angle in it, basically. And so these two angles don't really matter, but what it tells us is that the two sides, two smaller sides, A and B, and then the bigger side, C, so the hypotenuse. Okay, so this over here is and if you forgot this name, that's okay. We're bringing it back, hypotenuse. Okay, and A and B, these are what we call the legs. Okay, and so over here, what we have is, okay, so over here, what we have is we go based on the Pythagorean theorem. The Pythagorean theorem tells us that a squared plus b squared is equal to c squared. Okay, and so anytime I'm given a right angle triangle, I could look at the small legs and I can say, okay, based on the Pythagorean theorem, if I were missing, for instance, what c is, right? Like I know a and I know B, but I don't know C, then I can always just take those numbers and sub them in. So let's try it out. Let's say you're given a triangle like this. Okay, here's your right angle triangle. And you're given, for instance, you're given B is equal to 7. You're given C is equal to 9. And you're asked, what is this? What is this side? And they've labeled it as X. And they tell you, find X. Okay? If you ever have a scenario like this and you're asked, oh, find X, or you have something like this, and I can even change the numbers around, right? Like I can go, or let's just keep it right now. Okay, so what I can do here is I can say, well, I know that by the Pythagorean theorem, the smaller legs, so x squared plus the other small leg, 7 squared, is equal to 9 squared, is equal to the hypotenuse, the long leg, the long side squared. And so we know that 9 squared is equal to, if I were to continue this, we know that the 8 squared is 64, 9 squared is equal to 91. And you need to make sure that you know your perfect squares by heart, okay? All right, so 9 squared is 81, 7 squared is 49, and then we have x squared over here. Now remember, anytime I'm doing algebra and I'm trying to solve for a variable, I just move everything to one side and keep x on its own. And so I go x is equal to, move this to the other side. Now, there is no such thing as move it to the other side in math. The way I'm moving is I'm subtracting it, okay? And this is why you probably learned this before, where if you move something to the other side, you turn it into subtraction if it's addition, and if it was subtraction, then you turn it into addition. If it was multiplication, you turn it into division, and so on, right? You do the opposite operation. And that is what we're going to do. We're going to go 81. So x squared is equal to 81 minus 49. Bring that up here. We're going to have x squared is equal to 81 minus 49 is equal to 32. And so in order to find x, I'm going to go, well, I want to do the opposite. This is where I really, really need you to focus, okay? The opposite of something squared is the square root, okay? So that's what we were learning initially. What is the square root, right? Something squared is saying, oh, 9 squared, or saying, for instance, 2 squared, right? 2 squared gives me 4. Now, let's say I'm sitting at 4 and I want to figure out what number gives me what number squared gives me 4? Then I go square root of 4. So basically, they're opposite operations of one another. Let's write that rule down. Squares and square roots are opposite operations. Okay. And what that means is that if I ever have a square and I want to get rid of that, did you see how we got rid of this 49 by subtracting both sides by 49? If I want to get rid of the square, I do the opposite operation, just like I did with the 49. The opposite of addition was subtraction. The opposite of square is square root. And so I square root both sides. These two cancel out because they're opposite operations. And I'm left with x is equal to the square root of 32. But 32 is not a perfect square. 32, however, sits between 25 and 36. It's a little bit closer to 36, 4 units away, and from 25, it looks like it's 7 units away. And so I'd say it's around, like, if we were to draw a number line, right? And here is, for instance, 0. This is our 5. This one is 6. So this is the square root of 25, square root of 36. It looks like square root of, like in the middle, what's the difference between those? So that's 5 unit, like between 36 and 25, that's 11 units. And so the middle part, this 5.5 would be like 5.5 units away. And so like it would be 30.5, okay? But we're sitting at 32, so it's a little bit on this side. So I'm going to say like it looks like it's a 0.7-ish. So I'm going to say this is approximately 5.7. Okay, and we can test this out. We can put it on a calculator. Now, if you're not allowed calculators, you can just do it like that. but you can also test it out. You can go, okay, what is 32 squared? Okay, so I get 5.65, which could round to 5.7, or I could leave it at 5.6, whichever. They're both are good estimates, okay? And so this is pretty much it for the Pythagorean theorem. As long as you know this relation over here, you just do it for whichever you need. So for instance, in this case, we needed A, but maybe the next time we need B. Maybe the next time we need C. So we just put what we know and then isolate and solve for whatever we don't know. Okay? All right, everyone. So that's it for square roots of non-perfect squares. I'll see you in the next video. Bye.